Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This module number 1, lecture number 5, Introduction to Reinforced Earth. I will now address the recap of the previous lecture. What we have covered so far: standard analysis of reinforced earth, internal local stability, critical slip surface of inextensible reinforcement, that means metallic reinforcement, critical slip surface of extensible reinforcement, that means polymer reinforcement or geogrid. Then calculation of maximum tensile forces in the reinforcement layer. We have also partly covered on design and inextensible steel reinforced soil retaining wall. So far we have partly shown the failure mechanism of reinforced earth wall. The potential failure mechanism of reinforced earth wall, one is the sliding, which I have covered, and the sliding is like this. If this is the RE wall and this is the reinforcement. So, initially we calculate the what will be the factor of safety due to sliding. So, this is the sliding. This is one of the potential external failure mechanism of reinforced earth wall, and this is the reinforcement. So, reinforced structure may slide on this direction. So, that is why you require something force on this direction to resist it. So, it may be designated as F of R. So, earlier we have calculated this what of the factor of safety due to sliding. So, this we have already covered, that what will be the factor of safety against this sliding. Apart from this sliding failure, there are also potential failure due to the overturning as well as due to the bearing capacity. So, what will happen in case of overturning? Now, we will go to the problem for the overturning. This is the reinforcement, this is the wall, so here is the reinforcement. Now, this wall may overturn, so this is overturning. Now, this overturning, due to the overturning, this reinforced earth wall may collapse. So, we have to calculate what will be the factor of safety against overturning. We have considered the reinforced soil retaining wall with a uniform surcharge. This is the external overturning stability of a reinforced earth retaining wall with a uniform surcharge loading. So, we have to calculate what will be the factor of safety due to the overturning. So, factor of safety due to overturning can be defined as summation of moment resisting moment resisting this divided by moment summation of moment overturning. So, we have to calculate this factor of safety, that is the ratio of summation of moment resisting and ratio of summation of moment overturning. And apart from this failure, we have the bearing capacity failure, that means some kind of the foundation problem. So, in case of the bearing capacity problem, so if this is the wall and this is the reinforcement, number of layer of the reinforcement, So, this is bearing capacity. Bearing capacity. So, foundation may fail due to the bearing capacity. So, you have to calculate that what should be the factor of safety against this bearing capacity. Apart from the bearing capacity failure, there is also potential rotational slip surface failure, but we are not considering in this problem the rotational slip surface failure. So, I am just showing that one of the picture, draw this reinforced soil wall, and this is the reinforcement, this is the reinforcement, and structure may collapse like this. So, that means this is called the rotational slip surface failure, or it called also the global stability or deep seated stability. So, when the failure surface pass behind the reinforcing material, you can see that reinforcement is here, but this slip surface passes behind the reinforcing material. So, there is a possibility for the global failure or rotational slip surface failure. This just I am showing one of the failure may occur, and so we will initially talk about the overturning failure. So, what should be the factor of safety against this overturning? To understand this overturning failure, we have to consider the what should be the eccentricity. That means you have to calculate the eccentricity or at the base of the foundation. So, I just show you some picture regarding the potential failure mechanism of external stability failure due to some surcharge loading. We saw that how the structure can fail due to the sliding, and we have calculated the what will be the factor of safety due to sliding. Now, we will address that what should be the failure due to the overturning. That means what should be the factor of the safety due to overturning, that is what should be the ratio of the moment resistance to the moment overturning. Now, when we will show that overturning, we have to calculate that what should be the eccentricity. So, this is at the base of the foundation and length of the reinforcement is L, and L minus 2 is which is the acting zone, and this is the stresses on the foundation soil, and there is also the vertical stress which is defined as sigma of B. You have to calculate what should be the eccentricity. So, eccentricity E is equal to L by 2 minus MR minus MO divided by W of R. Now, what is MR? Mr is the resisting moment, that means that is equal to Wr into L by 2. So, it is like this is the wall and this is the length of the reinforcement is L and Wr is weight which is acting vertically downward. If we take a moment at the toe of the wall, so this moment will be Wr into L by 2. This Wr is acting at the middle of the reinforcement. So, this is Wr into L up 2, which is shown Mr is equal to Wr into L by 2. So, we have earlier calculated that what will be the W of R. We have already calculated, we know the length, we know the height, we know the gamma. So, we can calculate what will be the W of R. So, which calculation I have shown earlier 1077.3 and this into L by 2, that is 6.3 and that is coming resisting moment 3393.495 kilonewton meter per meter. Now, we will calculate the overturning moment MO, that means what are the forces are acting on the wall. So, there is a Fa and there is a Fq. Fa is the forces due to the soil pressure, Fq the forces due to the surcharge load. So, here this is the Fa, this is the soil pressure, these are all the forces acting on the reinforced soil wall. So, this is the forces Fa which is acting at a distance of h by 3. So, moment will be Fa into h by 3. So, that is why it is shown that Fa into h by 3. You know that it is acting at the 1/3 of the height of the wall and plus the force due to the surcharge load, that is Wq, which is the force is represented here as Fq, that is surcharge pressure. Now, this surcharge pressure is acting at the middle of the wall, that means height of the wall is h, then this height will be h by 2. So, this moment will be Fq into h by 2. So, total moment will be this into Fa into this distance h by 3 plus Fq into h by 2. So, this moment MO will be Fa into h by 3 plus Fq into h by 2. So, Fa we have already calculated, this is 256.5 into h by 3 is 9 by 3, height of the wall is 9 meter and Fq we calculated earlier 30 and h is 9. So, 9 by 2. So, if we calculate we can obtain 904.5 kilonewton meter per meter. So, we have calculated this Mr as well as M0. Now, we have to calculate eccentricity E. So, this eccentricity, if you know that eccentricity, we can calculate what will be the L minus 2E. We know the length, but we do not know the value of eccentricity. So, eccentricity can be expressed as L by 2 minus Mr minus M0 by Wr. So, L is 6.3 divided by 2 minus Mr is we have already calculated, this is 3393.495 3393.495 minus M0 is 904.5. So, 904.5 this divided by this weight Wr, which we have calculated earlier. So, WR is equal to 1077.3. So, if we calculate this, we can have 0.839, so which is less than L by 6, that is 1.05. So, there will be no development of tension at the base of the foundation soil, then it is okay. Now, ultimately we have to calculate what will be the factor of safety against overturning. So, factor of safety against overturning is equal to MR by M0. So, MR is known 3393.495 divided by M0 is known 904.5. So, 904.5, this will give 3.75, and it should satisfy the criteria that it should be greater than 2. So, it is greater than 2, that means it is okay. So far we check up with this factor of safety against this overturning, that means we took this moment resistance by moment overturning and it is greater than 2. So, it satisfies the criteria. So, it is okay, design is safe in terms of the overturning. Next we will talk about this bearing capacity. What will be the factor of safety against this bearing capacity? So, we will discuss this problem, that how we can calculate this bearing capacity at the foundation, okay, whether it is safe or not. So, this bearing capacity, in this bearing capacity calculation we should know what will be the effective length. So, effective length is L minus 2E. So, you can see here, this is the effective length, this is the stress on the foundation soil. So, this is the measure of distribution. Okay, this measure of distribution is recommended for the stress on the foundation soil. So, this is the acting zone, this L minus 2E. So, that is why the effective length will be L minus 2E. What will be the vertical pressure over the foundation soil, that is we have to calculate sigma V. So, this is the sigma V, okay. This is vertical stress which we have to calculate, and which we have to calculate within this acting zone, that is L minus 2E, only this zone is acting as per measure of distribution. So, total vertical pressure over the foundation soil is designated as sigma V. So, sigma V will be equal to summation of V divided by L minus 2E. This is acting zone. So, summation of V means that is this summation of V, that is due to the weight and due to the surcharge. So, we can write that summation of V, that is weight WR, and it is surcharge W of Q, and this is L minus 2E. So, we can write sigma V, WR we calculated 1077.3 plus WQ we calculated 63, and this L is 6.3 minus 2 into E we calculated 0.84. So, sigma V will be equal to 246.78 kilopascal, which is less than 300 kilopascal, which is given. So, it is okay. So, given the allowable bearing capacity of the foundation soil is 300 kilopascal, so it is less than the 246.78, that means it is okay. So far we talk about the external stability of reinforced earth retaining wall. Now, we will discuss the internal stability. So, for this internal stability, the complete calculation along the entire height at each reinforcement level are presented in a tabular form at the end, but here I am just showing one hand calculation for the internal stability are performed at a depth z is equal to 4.875 meter. You can assume any of the depth, but I have considered one typical value of depth, that is z is equal to 4.875 meter. So, calculate this internal stability. So, we have to calculate what is the K of AR, coefficient of active path pressure. KR is equal to tan square 45 degree minus pi r by 2, and pi r value is 32 degree is given. So, it will be tan square 45 minus 32 by 2 is equal to 0.307. Now, here you look that Z is less than 6 meter. So, we consider Z is equal to 4.875 meter. So, from the interpolation we can calculate this KR is equal to KAR 1.2, 0.5, 6 minus Z by 6, that will be equal to 0.398. I will show you how we have calculated KR is equal to 0.398. Now, from this figure, so we have to calculate, this is the metal strip we have used, and we know that KR by KR is 1.2 to 2.6, and we have to calculate for this zone 1.7, this is a metallic strip, red color zone, and this you know that after the 6 meter depth is remain constant, this is the depth 6 meter depth will remain constant. So, we can see that 1.2 and 1.7. So, in between at any depth you have to find out, and then you can calculate that what is KR by KR is lying. So, if we consider like and that you have seen that this is, let us say, 1.7 and this is 1.2, okay, and this is about 6 meter, okay. So, what I wanted to show here that this is 1.7 and this is 1.2 and this depth is 6 meter and this is x, and so this portion will be 1.7 minus 1.2, that means this will be 0.5, and this at a depth of z, this is x. So, the remaining portion will be 6 minus z, because this is the 6 meter. So, this is 6 minus z. So, from this triangle, so we can to calculate what should be the value of KR for the z less than 6 meter. Here z is less than 6 meter. So, this from this triangle both you can calculate 6 minus z divided by 6 is equal to, this is 0.5, this divided by x. So, from this equation you can calculate x is equal to 0.56 minus z by 6. Now this is k r by k r will be equal to 1.2 plus x, that means 0.56 minus z by 6. You can see here this is 1.2 plus this is kr by kr. So this will be 1.2 plus 0.5 into 6 minus z by 6. So kr will be equal to kr 1.2 plus 0.5 into 6 minus z by 6. So we have to calculate what will be the kr at z is equal to 4.875 meter. So we have to substitute the value of z is 4.875 here. So you can calculate kr is equal to, we have calculated kr is 0.307, this is 1.2 plus 0.5 into 6 minus at a depth 4.875 meter divided by 6. So you calculate kr is equal to 0.398. So from this, that is why this at when the z is less than 6 meter, z is equal to 0.87 meter. From the interpolation we calculate kr is equal to 0.398. Okay, so you know that how to calculate this kr from this diagram. Now at this level you have to calculate the vertical pressure, that is sigma of V. So sigma V is what will be the gamma r into z plus q is the surcharge load. Density is 19 and depth you know 4.875 and plus surcharge is 10. So vertical pressure sigma B is equal to 102.625 kilopascal. So if you know that vertical pressure, you can also calculate that horizontal pressure sigma h, because you know sigma h is equal to kr into sigma V, that means vertical pressure. So kr you have calculated 0.398 into sigma V 102.625. So horizontal pressure will be 40 into 795 kilopascal. Now if consider the tributary area AT over the twice the panel width to determine the horizontal spacing among reinforcement. So tributary area AT can be defined as 2 into panel width into SB, and panel width we have considered 1.5 meter. So 2 into 1.5, and spacing we have considered 0.75. So therefore AT, that tributary area will be the 2 into 1.5 into 0.75, that will give 2.25 meter square. Now you know maximum horizontal forces on the tributary area, that is T maximum, will be equal to horizontal force sigma h into AT. That means what will be the tributary area. So sigma h is 40.795 into area AT is 2.25, that is 91.789 kilonewton. So we have to consider that factor of safety against the pull out failure, that is Fs pull out, it should be greater than equal to 1.5. For all internal stability you have to check what will be the factor of safety against pull out. So pull out resistance, which is designated as PR, which should be greater than equal to 1.5 into T. T we have calculated 91.789, so that will be equal to 1.5 into 91.789, 137.683 kilonewton. Now, if you consider the minimum number of the reinforcement required in the tributary area to achieve the pull out resistance, that is N. So, N will be equal to PR divided by 2 into B into F star into LE into sigma V dash, where B is the width of the reinforcement strip and that is 50 millimeter, LE is the embedment length of the reinforcement, that means L minus L of A, and sigma V is the vertical pressure ignoring the surcharge pressure. You can calculate the F star and that depend upon the what will be the value of coefficient of uniformity of the soil, that is C of U. So, F star can be calculated by the equation F star is equal to 1.2 plus log Cu at the top of the structure or equal to 2 the maximum, or F star is equal to tan pi r at depth z greater than equal to 6 meter. So, when you want to calculate the F star and that depend upon the what will be the soil characteristic at that locality and that depend upon that C value, that means what will be the coefficient of uniformity of the soil, and that maximum value you can take that 2 value. And if the depth is greater than 6 meter, so you can take F star is equal to tan of pi r. So, next slide will show that what will be the variation of friction factor F star with the depth. So, you can see here this is the depth of the wall and this is the friction factor and this is tan pi r, this is tan delta and this is the strip, and what pi r is internal friction angle of soil in the reinforced zone and delta is the friction angle between soil and the reinforcement. Now, in this figure is show that variation of friction factor F star with the depth. Now, in our problem we find that depth Z is less than 6 meter. So, therefore, we have to calculate F star by from interpolation. So, this F star can be calculated as here Z is less than 6 meter. So, you can see that this is the depth, this is 6 meter, okay, and in this here it is 2, here it is tan of pi r, and at any depth, let us say this is x. So, we are considering at a depth that is z. So, this will be equal to 6 minus z, 6 minus z, and this difference will be equal to 2 minus tan of pi r. So, from this triangle we can write that x divided by 6 minus z is equal to 2 minus tan pi r, this divided by 6. So, we can write x this divided by 6 minus z, 6 minus z is equal to 2 minus tan pi r, that means 2 minus tan of pi r, this divided by 6. So, we can calculate that x will be equal to 2 minus tan of pi r divided by 6 into 6 minus z. So, we can have this relationship, that is x is equal to 2 minus tan pi r by 6 into 6 minus z. So, we can now calculate that when the z is less than 6 meter. So, we can also show here that f of star, and remember that z is less than 6 meter, and from this interpretation you can write f of star is equal to tan of pi r. Then we can consider from here 0, then it will be the tan of pi r, and plus 2 minus tan of pi r by 6 into 6 minus z. So, we know that what will be the value of pi r? Pi r is equal to 30 of 2 degree, okay, and z we know that we want to calculate at a depth of z is 4.875. So, at this depth we want to calculate what will be the f star. So, we are substituting this value pi r, then tan 32 degree plus 2 minus tan pi r is 32 degree divided by 6 into 6 minus z, z is equal to 4.875 meter, which is less than 6 meter. So, from this equation you can calculate that what should be the f star value. So, this f star value will be equal to 0.883. So, this we are having 0.883. Okay. So, we are having this value of f star. Now, as the depth is greater than h by 2 or is equal to 4.5 meter. So, you have to calculate what will be the length of the reinforcement in the active zone. So, you have to calculate the length of the reinforcement in the active zone. So, length of the reinforcement in the active zone is 0.6 h minus z. This also you can calculate from the interpolation. That means 0.6 into 9 is the height of the wall minus z at a depth of 4.875 is equal to 2.475 meter. So, we can calculate 2 into 0.475 meter. So, now you have to calculate this length of the reinforcement in the active zone. So, length LE is equal to L minus L of A. So, you calculated what will be the length of the reinforcement active zone, that means L of A is 2.475. So, LA is 2.475 and L is 6.3. So, this minus this will give 3.825 meter. So, sigma V dash, that is vertical pressure at the level ignoring the surcharge pressure, will be equal to 102.625 minus 10. So, this will give 92.625 kilopascal. So this N equal to PR divided by 2B F star LE into sigma V dash. So we have calculated PR earlier, that is 137.683, 2 into B width of the metallic strip 0.05, F star we calculated 0.883, LE we calculated 3.825 into sigma V dash, which we have calculated 92.625. So N is equal to 4.403. So we have to consider this N as a round figure, and of course here I just wanted to mention that how we have calculated that LA is equal to 0.6 H minus J from the interpolation. I am showing in this figure. This is in the active zone. If you know that the length of the wall is H, so this will be 0.3 times of H, that means this is 0.38. This is in the active zone. And you know that in case of the metallic reinforcement, it is bilinear kind of the failure. It goes in the half of the height of the wall and then it straight. So we have to calculate at this level, at a level of Z, what should be the active length, that means LA, because that our Z value is greater than H by 2. That is why we have considered some typical value, that is 4.875 what we have considered, which is behind the H by 2. So for Z H by 2, so at this depth Z we have to calculate LA. So what will be the Y value? Y will be equal to Z minus H by 2, and this is 0.3 H, this is 0.3 H divided by H by 2 is equal to this LA divided by H by 2 minus of Y. So from this we can have 0.6 is equal to LA divided by H by 2 minus Y. So LA will be equal to 0.6 H by 2 minus Y. So LA will be 0.6 into H by 2. Again Y is equal to, this is Z and this is H by 2. So Y will be Z minus H by 2. So Z minus H by 2. So we can have LA is equal to 0.6 H minus Z, which we have shown here. LA is equal to 0.6 H minus Z. So that way we calculated the what will be the LA value. Hence the N actual is 5, it should be an integer value. So we have taken a round up figure, N is actual 5. In the tributary area, 5 number of strips should be provided in a row. Approximate horizontal spacing H can be 2 into panel width divided by N, 2 panel width 1.5 meter, that means 2 into 1.5 divided by N, round figure 5. So you can have the SH value, horizontal spacing is 0.6 meter. Now we have to calculate that what will be the corrected pull out resistance, PR actual. So PR actual will be equal to 2 into B into F star into LE into sigma V dash into N actual. That means 2 into 0.05 width of the strip, LE value, F star value we have calculated 0.883, sigma V is equal to 3.825 LE into this value 92.625 into 5 sigma V and N. So ultimately you calculate that PR actual is 156.367 kilonewton. So you have to calculate what will be the factor of safety against pull out failure. So, pull out failure factor of safety against pull out failure will be equal to PR actual divided by T. So, PR actual 156.367 divided by 91.789, that means 1.705. So, it is greater than 1.5, that means factor of safety against this pull out failure is okay. Now, in step 4 we will calculate the stress in the metallic strip during design life. So, initial thickness of the metallic strip reinforced made of steel including the zinc coating of 0.086 millimeter is equal to 5 millimeter. According to Federal Highway Administration's FHWA 1990, the thickness losses per year are as follow: zinc loss 0.015 millimeter per year first 2 years, and then 0.004 millimeter per year thereafter. Steel loss 0.012 millimeter per year per site thereafter. So, now we have to calculate that what will be the time required for complete zinc loss. Time for complete zinc loss is equal to 2 years plus 0.086, that is initial loss which is been given, minus 2 into 0.015, that is zinc loss, that zinc loss 0.015 millimeter per year first 2 years. So, 0.015 into 2 divided by, that is 0.004 millimeter per year thereafter. So, this will be the 0.004. So, if you calculate then complete zinc loss, it takes time about 16 years. So, steel loss will be, this is a 75 year minus 16. So, 59 years during the design life. So, what will be the total thickness loss during design life, that is designated as T loss. So, T loss will be the 2 into 0.012 into 59 years. 0.012 is the steel loss 0.012 millimeter per year per side thereafter. So, it is a both side, therefore 2 into 0.012 for the year 59 years, that means 1.416 millimeter. So, remain thickness T remain will be the 5 minus 1.416, that means 5 millimeter thickness we consider for steel strip. This minus this will be 3.584 millimeter or 0.003584 meter. So, remain cross section after the design life for 75 years, that is A C will be equal to 0.003584 this thickness into this 0.05, that means 0.00017992 meters square. Now, we are considering the steel strength is Fy is 413.7 megapascal for 60 gauge steel. So, you have to calculate what will be the allowable. So, allowable will be 0.55 into Fy is equal to 227.5 megapascal. So, tensile stress Fa in each strip can be defined as T divided by Na into As, that means T is 91.789 divided by N is 5 and As calculated 0.00017992. So, this will give 102.4 megapascal, which is less than 227.5 megapascal, that means it is okay. So, here for this entire detailed calculation, we know that what is the panel width 1.5 and tributary area, what will be the strip thickness 0.005 millimeter. Here I am showing only one calculation, which is at a depth of 4.875. We calculated what will be the vertical pressure in kilopascal, what is Kw, what is Kr, what will be the horizontal pressure in kilopascal, you have calculated F, you have calculated La, you have calculated Lr. So, if we combine this, then we can have this, what will be the total length, and maximum force is this, and what is Pa in kilonewton, N number is 4.5, we make a round figure is 5. So, you have calculate what will be the horizontal spacing, then the what will be the pressure, what will be the tensile stress, and what will be the factor of safety. So, I have shown only one calculation, and accordingly you can calculate at the different depth and can design the metallic reinforced soil retaining wall. Now, we can see that there are defined types of the system in the conventional method: gravity retaining wall, cantilever retaining wall, steel pile wall, or the braced excavation and soil nailing. So, alternative to this system, that this is the Beetle Vision, how he has developed the mechanically stabilized reinforced earth wall using the metallic strip. So, he used this is the metallic strip, this is the facing element, this is the length, this is width of the strip, and there is also the horizontal vertical spacing, also the horizontal spacing, and you can make a defined types of the facing element. So, when you go for this kind of the metallic reinforced earth retaining wall, so most of the cases, as metal is very costly, this will be the high cost, and it is a long term susceptibility to corrosion because it is a metallic reinforcement. That is one of the disadvantage of this kind of the material, and also at the same time the sustainability depend upon the correct choice of the backfill material, and it depends upon the gradation and chemical properties, etc. Because it is the metal, so you have to select proper kind of the gradation material, and it cannot be used all the time as a indigenous material, and in general the backfill material cost is about 30 to 40% of the total cost of the reinforced soil wall. So, sometimes it is preferable to use the non-corrosive material like polymer geosynthetics material as reinforcement. I am not trying to say that you cannot use this metallic reinforcement. Metallic reinforcement can be used, but one has to be careful for using this metallic reinforcement because it has some corrosion effect, and because polymer, one advantage is that this polymer does not corrode, and also it is economical, also used with the many other indigenous material. Also some disadvantage that it is a creep factor, and also it will be careful about the sunlight or vandalism. So, with this I ended up this today's lecture. Please let us hear from you any question, and thank you for listening.